Sound waves, seismic tremors, and ocean swells share a physical prerequisite. They require matter. Mechanical waves transfer energy through a medium via molecules physically colliding. Electromagnetic radiation ignores this physical restriction. It travels through the absolute vacuum of space, entirely independent of any molecular lattice or fluid medium. In a vacuum, this radiation propagates at an absolute invariant velocity of roughly 300 million meters per second, the speed of light. Without matter to physically push against, an oscillation must occur within another physical mechanism to transport this energy across the observable universe. Electromagnetic self-propagation is a geometric requirement dictated by 4 specific coupled mathematical rules. These are Maxwell's equations expressed here in their modern differential vector form. They serve as the foundational axioms of classical electrodynamics. To understand how light actually moves, we must map these 4 operators to physical geometry, beginning with the behavior of fields that are completely stationary. We begin with Gauss's law for electric fields. The inverted triangle with a dot is the del dot operator, which calculates a property called divergence. Divergence measures a field's tendency to originate or converge. Place a positive point charge in a 3D grid. Electric field vectors diverge outward, acting as a source. Conversely, a negative charge acts as a sink. Field lines flow inward, terminating on the physical charge itself. Gauss's law for static magnetic fields applies the exact same divergence operator, but the result is 0. A divergence of 0 dictates a severe geometric constraint. Isolated magnetic charges, or magnetic monopoles, do not exist in the universe. Without a source or a sink to begin or end on, magnetic flux lines are forced to form continuous, closed loops upon themselves, with no point of origin. In this static regime, fields cannot escape. Their existence is permanently tethered to the physical presence and geometric shape of the charges or magnets generating them. In the early 19th century, Michael Faraday demonstrated experimentally that electricity and magnetism could directly influence one another through motion. This dynamic relationship is formalized in Faraday's law of induction, introducing a new mathematical operator to the framework. The del cross symbol represents the curl operator. Instead of measuring outward flow, curl measures exactly how much a vector field swirls or circulates around a specific point in space. On the other side of Faraday's equation is a time derivative, requiring the magnetic field to change over time. When paired, a changing magnetic field induces a circulating electric field, generating a non-zero curl. This induced electric field behaves differently than static fields. It loops back on itself, possessing no physical point of origination or termination. Faraday proved that an electric field can exist independent of physical charges, provided it is continuously driven by a dynamic magnetic environment. The final piece of classical electrodynamics was Ampere's circular law. In its original form, it stated that a circulating magnetic field is produced by an enclosed electric current. We can test the limits of this law with a simple thought experiment. Consider a direct current circuit containing a battery, a switch, and a parallel plate capacitor. When the switch closes, electrons flow through the wire, accumulating charge on the plates. We define an imaginary boundary loop, C1, wrapping around the copper wire leading to the capacitor. The current density pierces straight through the flat surface bounded by this loop. Because electrical charge flows through this surface, Ampere's law accurately predicts the magnetic field observed circulating around the wire. But if an identical loop, C2, is shifted into the gap between the capacitor plates, the geometric conditions change. The area bounded by this second loop contains absolute vacuum. Because no physical charges flow through a dielectric vacuum, the enclosed electrical current at C2 is mathematically 0. This creates a direct contradiction. Despite the equation yielding a 0, physical instruments placed inside a charging capacitor gap measure an active circulating magnetic field. Ampere's original law failed to account for this gap, creating an inconsistency with the principle of conservation of charge. In its original form, the equation was mathematically incomplete for vacuum environments. In the 1860s, James Clerk Maxwell sought to unify the experimental observations of Faraday and Ampere into a single, cohesive mathematical framework. He identified the missing term in Ampere's equation and added a crucial variable, the displacement current density. Displacement current is the mathematical rate of change of the electric field over time. In the absence of moving electrons, this varying field fulfills the role of a physical current. As the capacitor charges, the electric flux between the plates increases. Maxwell's addition established that this changing electric flux induces the missing magnetic field circulation, restoring mathematical continuity across the vacuum gap. With this single term, Maxwell locked the universe into a precise mathematical symmetry. Changing magnetic fields create electric fields, and changing electric fields create magnetic fields. We can observe the physical consequences of dissymmetry by applying it to an accelerating charge, like an electron oscillating in a linear radio antenna. In the near-field induction zone surrounding the antenna, the fields are dominated by static components. These fields store energy locally and decay rapidly, dropping off as the inverse square of the distance. In the outer radiation zone, the dynamic terms take over. Because the changing electric and magnetic fields are mutually inducing one another in a constant cycle, they decay more slowly. These orthogonal waves detach from the local static field, pushing outward into the absolute vacuum. Electromagnetic radiation is the direct mathematical consequence of a changing electric field taking over the job of a physical current, allowing energy to sever its connection to matter. By transporting energy at a finite relativistic speed, these detached waves carry momentum despite having zero mass. When an electromagnetic wave strikes a physical surface, it transfers this momentum to the object. On a large scale, this exerts tangible mechanical force known as radiation pressure. Special relativity further clarifies this process, showing that electric and magnetic fields are interwoven components of a single four-dimensional electromagnetic field tensor. Whether an observer measures an electrical effect or a magnetic one depends on their specific relativistic frame of reference. The remnants of the early universe provide empirical confirmation of Maxwell's self-propagating vacuum equations. In the 1960s, astronomers using the Holmdel-Horn antenna detected a faint, uniform signal arriving from all directions. This is the cosmic microwave background, the first free-traveling photons released during the recombination epoch, 13.8 billion years ago. This heat map from the WMAP satellite captures the slight temperature anisotropies of the oldest light in the universe. Over billions of years, as the universe expanded, the wavelengths of these ancient photons stretched, shifting them into the microwave spectrum. These ancient photons have traveled across the universe for billions of years without a physical medium to carry them. The visible light we see, the wireless data we transmit, and ancient cosmic thermal signatures exist because James Clerk Maxwell identified a mathematical gap, added the displacement current, and allowed energy to fly free.